Hello and welcome everyone. I recently started preparing my next video and halfway realized the challenging technical intro would scare away my few remaining viewers. I therefore decided to split it in two. Today I'll do the scary intro, you ignore. Later I'll make the actual backgammon content nobody watches. And eventually I'll post a simplified summary, which might be useful to someone. But it's riveting stuff, I assure you, for anyone planning to write backgammon software. Anyway, today I'll talk about bootstrapping Cubeful equities, or more precisely, computing Cubeful money equities for race positions. I already described how to compute exact equities for bear-off, and would have loved to do the same for pure race positions. Alas, race is a million times bigger than bear-off, and we must abandon absolute truth and settle for inhumanly strong bot estimates. And when constructing such a bot, it helps to understand why bots are so strong. It boils down to two dependent factors plus one lucky coincidence, which I'll call magic, speed, and relativity. First comes magic. Bot performance hinges on static evaluation, the ability to estimate win and gammon rates by just looking at the checker's positions. This is, you must agree, magic of the highest degree, performed by the digital wunderkids of our time, neural nets. Static evaluation is already very strong, but it's not enough. Next comes speed. Nanosecond computations allow bots to see into the future, to play out the position for all rolls or some of them at some specific depth, be it one move ahead, two, or even until the end of the game, and then average all those branches and pick the action with the best expected outcome. Traveling into the multiverse reveals long-term features, which static evaluation might miss. And lastly, relativity. Bot evaluation doesn't need to be absolutely correct. If move A wins 80% of the time and move B 70%, it's enough if the bot says A wins 50% of the time and B 40%. That is, enough for the bot to prefer A over B. So usually we're happy if the bot simply ranks positions correctly. This breaks down only in one place. The drop point is fixed, so you need a good absolute estimate for the take-drop decision. Now, speed I kind of have, and relativity is always there. So, we mostly need to figure out static evaluation. It's a multi-stage process, but quite straightforward for someone of my experience. We start with what we know, namely that cubeless evaluations generate extremely accurate cube decisions for bear-off. However, a decision is not enough. We want the actual equity values. So let's plot Cubeful equity of bear-off positions, which we know how to compute, as a function of the cubeless probability. And it's a pleasant graph. The cubeless win probability is highly correlated with Cubeful equities, be it no double, shown in blue, or double take, shown in orange. So, we can get a leg up by fitting a piecewise linear function to each of the three types of equities and use those functions as basic static evaluation. Let's call it BOP, with a 0, basic zero-ply equities. Here, for example, black's winning chances are 40%, so we raise a line upward from the x-axis at 0.4 and mark where it hits the piecewise curves, thus giving us the three Cubeful values. All fine and dandy, but note, we gained nothing in terms of decision making. Both is equivalent to a fixed doubling window, which starts where the no double and double take lines meet, and ends where the double take hits 1, the drop value. So here, speed kicks in. In this position, black wins 69.1% of the time. So it sits right at the edge of both no double range, yet it's a huge double take. Luckily, by using one-ply evaluation, that is, by looking at all positions after black rolls the dice and makes a move, boss can see that not rolling a 1 always brings black into the double drop range. That is, not rolling a 1 will likely produce a market losing sequence. If white doesn't roll a joker, black will double out white. And that's enough to push the expected values into the double take range. And with 2-ply, making one move for black and one move for white for all possible dice combinations, the numbers get closer to the true values. They'll always be off, but remember relativity. Accurate numbers are secondary. It's correct decisions we're after. And 2-ply, which directly examines 441 positions, can count market losers more accurately and thus make better decisions. So good, in fact, they can be used to train a neural net. A neural net which spits out the 3 cubeful equities directly from the position without going through the cubeless equity. This first generation net produces, for our position, a static evaluation much closer to the truth than the Boss 2-ply. An FGN is a real improvement over Boss. This new position has the same cubeless win probability for black, 69.1%, but it's a no double take. Boss, by design, has the same no double verdict, which is now correct, but so does FGN static evaluation. Boss always calls positions with 69.1% the same way, but FGN can go either way, and when trained with the right data, we'll get it right more often than Boss. And this net generating process can be iterated. Just take 2-ply evaluations of an FGN and use them to train a second generation neural net. And that's what we're going to use today. 2-ply evaluations of an SGN. It's far from perfect and can surely be improved, but strong enough to provide a good overview of the landscape. And what do I mean by landscape? Look at our pair again. The same cubeless win percentage, yet different cube actions. Why is that? Can we find a general pattern? One simple candidate literally springs to mind. One position is going to last 3 to 6 rolls, and by rolls I mean the total made by black and white, while the other will run for a while. Can we validate this intuition using data and maybe learn something? First, we need to quantify this idea of time to finish, TTF. I started with the minimum of A, black's pip count minus 8, and B, white's pip count, 8 being the average pips black is about to gain. Here's a plot of this move-adjusted pip count against the estimated TTF obtained from rolling out the position. The variance is large, like most backgammon quantities, but there's a clear linear relation. So this measure can work, but I found something better. Look at positions A and B. Black leads the race with 50 pips after subtracting 8 in both A and B, so both fall into the same bin. However, A takes on average 3 rolls more than B to complete bear-off. Why? Again, there's one obvious candidate: wastage. Those checkers near the edge will waste pips when born off with high dice. And true enough, if we define wastage as the total number of checkers on the 1 and 2 points, and plot wastage against TTF for positions with the same adjusted pip minimum, we can see a clear linear relation. And if we do the same for all bins, it turns out the linear fit parameters, slope and intersection, have a very nice linear relation themselves to the adjusted minimum, which gives us the following simplified TTF approximation, which nicely puts A and B in different bins. So using this approximation to lump together positions with similar lifetimes, I generated this wonderful but challenging plot. Each point represents one position, and there are about 500,000 of them, obtained by playing out races. So they are a sample of positions you might encounter in your own games. The position's X value is the TTF, the number of moves to finish given by the estimate, and the Y-axis value is the cubeless win probability. Each position is colored by its own action: no double in yellow, double take in green, double drop in red, and too good in magenta. So now we can determine the doubling window for each of those bins, that is, the double and take cutoffs based on both TTF and the cubeless win probability. And as you can see, the window location depends heavily on the TTF. No big news, but the magnitude going down from 69% to 60% when the TTF goes down from 12 to 3, that's something. Binning positions by TTF can help us answer questions like, does the work we did with Beroff cubing formulas applicable to races? So here's the same plot, only now there are two doubling windows. A doubling window for race in black and a doubling window for Beroff in blue. And while there might be a small difference around TTFs 13 to 17, it seems that positions with the same TTF share the same window or the same doubling urgency, whether they are Beroff or pure race. Here is another example of landscape visualization. I recently heard Mochi mention the well-known adage that a player on roll can offer an initial cube when leading the race by 8 or 9% pips. So here's a plot of black versus white pip count, where the no double positions are colored red and double positions are colored blue. And the yellow line, which marks the 8% divide, indeed fits with this sentiment. However, please remember that pips-only methods are quite weak. You must consider other factors like the wastage and TTF to get good decisions. And that's basically it, folks. A lot to take in, I know, but A, you can watch again tomorrow and maybe understand more. B, tap yourself on the back for being the first to reach the end of this video. Or C, just appreciate the time and effort needed to build tools even for so-called simple cases like pure race. And no matter how good, any tool still makes lots of mistakes, something you discover only by analyzing positions deeper, either using high applies or rollout. But that's for another day, maybe. See you again in part 2. Adieu.